Alright, here we go. Last projectile motion problem going to work out here, hopefully. A golfer's, it's the team sheet number 5. Projectile motion team sheet number 5. A golfer is teeing off on a 170-meter long par 3 hole. So that's going to be a horizontal distance of 173 meters. Let's get creative, draw our flag, and that's our ball. Huh? Okay. The ball leaves the velocity of 40 meters per second at 50 degrees. So I'm going to draw my vector down here. 40 meters per second at 50 degrees. As always, we need to break this down into our horizontal and vertical components. Any other details that we need? 50 degrees, 40 second. Assuming that she hits the ball on a direct path to the hole, how far from the hole will the ball hit the ground? So essentially, we're being asked to find dx. How far is this ball going to go? How close will it be to 173 meters? So we're going to see some sort of path it's going to hit. We want to know how far here is it from the hole. And so this distance here, that's our dx. Okay, let's break this down. So SOHCAHTOA, as per usual, sine of theta is equal to opposite over hypotenuse sine of 50 degrees is equal to opposite is, that's going to be our Vy. This right here is our Vx. So sine of 50 is equal to opposite that 50 degrees is our Vy. Vy over hypotenuse, which is, I was about to write hypotenuse there. 40 meters per second is our hypotenuse. 40 meters per second. Alright, so if we go ahead and we multiply by 40 to solve for Vy, it's going to be 40 times sine of 50 equals Vy. 40 times sine of 50 equals Vy. Calculator action. 40 times sine 50. 30.64. So our Vy is 30.64 meters per second. Same thing over here with cosine. So our cosine of theta is equal to the length of the adjacent over the length of the hypotenuse. Cosine of 50 is equal to our adjacent, the length adjacent to our angle is Vx. Vx over our hypotenuse, which is 40 meters a second. 40 meters per second. Again, multiply by 40 to solve for Vx. 40 times cosine of 50 is Vx. Our Vx is equal to 40 times cosine of 50. 40 times cosine 50. 25.71. 25.71. Now if we think about that quickly, it makes sense that our x velocity is lower than our y velocity. Had this been shot at a 45-degree angle, right, that's 45 degrees would be halfway between 90, which is straight up, and 0, which is straight across. So 45 would give us an even Vy and Vx. Now because it's 50, it's being shot more up than it is out, and therefore, right, it makes sense that our y velocity is greater than our x velocity because it's pointed further up than it is out. Anyway, so we've got our Vy and Vx, and those are our initial Vy and Vx. As we know, our Vy will change because of gravity, right? And our Vx is constant throughout the entire trajectory of this projectile, this golf ball in this case. Okay, we need to find dx. I'm assuming we're going to have to solve for t. We're going to try something different here. So the last problem we did, we solved for half the time, which is totally fine. I'm going to solve for, actually I'm a liar. I will go ahead and also solve for that half time here, right? So we're going to say that we're looking from when the ball is struck until it reaches its maximum height, and we know that at the maximum height the vertical velocity is 0. So we're going to treat that, right? We're only looking at the first half of this trajectory. We're going to call this our VF, our VYF, and we're going to call this here our VYI. So our VYI is 30.64, and our VF is going to be 0 because at that maximum height, as we know, the vertical velocity falls to 0. Okay, so it's V2. So VF Y is equal to VI Y plus AT. So again, we're just trying to figure out how long it takes this initial velocity to fall to 0. So 0 meters per second at that halfway point. So again, we're just going from initial to halfway. We're not calculating the rest of this trajectory. So our initial y velocity is 30.64 meters per second. 30.64 meters per second plus a, which is negative 9.8. Negative 9.8 meters per second squared times our t, which we do not know, which is what we're solving for. I'm going to subtract this 30.64 and get negative 9.8 times t. I'm going to divide by negative 9.8 and get negative 30.64 divided by negative 9.8, which will give us t, which will give us 30.64 divided by 9.8, 3.12. So it takes 3.12 seconds for this initial velocity of 30.64 meters per second to drop to 0 meters per second, because for every second it travels, right, gravity is decelerating it by 9.8 meters per second squared. Rather, for every second it travels, it's being decelerated by 9.8 meters per second. Meters per second per second. Okay, so this is the half time, right? This is a t half, because the vertical velocity is 0 at its halfway point, at its peak. So again, if we double this, our t total will be 6.24 seconds. And again, we're going to use our dx equals vx times t. Your card, dx equals vx times t. Our dx we're solving for, so we do not know. Our vx I don't remember. Let's go back and check what our vx was. We got that from our component of the given velocity vector. Our vx was 25.71, and that's meters per second because it's a velocity. I forgot it already. I'm tired, guys. 25.71 meters per second. 25.71 meters per second times our time, which was 6.24 seconds. Dx is 25.71 times 6.24, giving us 160.43. 160.43, and that's meters. Again, meters divided by seconds times seconds. The seconds cancel out, leaving us with meters, which is what we want. That's the displacement. So this is how far the ball travels in this whole path here. It's 173 meters away, so it's going to be 173 minus 160.43, which gives us 12.57. Is that right? I believe so. Yes. Meters from the hole. Hooray!